Welcome students to your channel PRADIP Sir Classes as PSC, and today I discussed with a particular concept, that is application of Gauss's theorem. So write down application of Gauss's theorem. Application of Gauss's theorem. So students, just memorize the particular theorem, that is phi means net flux is equal to E dot ds. You have to take a closed surface integration. If suppose this is the charge and that particular charge is closed within a surface, and you can imagine it within, suppose you can take a football and you imagine that at the center of the football there is a charge Q. So that particular charge can create an electric field along the different direction, and you have to calculate that number of electric field lines of crossing the surface, and that will be Q by epsilon naught. So Q is inside, so the net charge enclosed within the surface by epsilon naught upon epsilon naught, and this is phi net. So this is Gauss's theorem, and you have to apply it to calculate electric field due to the different distributions of charge. First of all, application 1 is due to linear distribution of charge. Linear distribution. What is linear distribution of charge? And again I remind you that suppose a charge is distributed along that particular line. So when charge distributed along a particular line, then we can take lambda equal to total charge by total length. Total charge by total length, that is linear distribution of charge, and you can take element by element. If you want to calculate the amount of charge within that particular element, that this will be dq. So a small charge, small element can contain a small charge, but the density remains same. If you take that particular length, then you can see the charge. Suppose if I consider the charge is the amount of charge is 2 and plus, there are two signs, and then this amount is contained, and this, if that particular charge is uniformly distributed, then we can say that the charge density remains same if we divided q by the total length or dq by dl. So there is a charge distribution, and this is infinitely extended. And infinitely extended, you have to calculate electric field due to this distribution of charge at a point P. P is the observation point, and it is r distance apart from the linear distribution of charge. So you can take another heading as calculate electric field. Calculate electric field due to an infinitely linear distribution of charge. So calculate electric field due to an infinite linear distribution of charge applying Gauss's theorem. Okay, so this is the heading, and for linear distribution of charge, if students, suppose if q charge is given here and you have to calculate electric field at that point, then it is too easy. E equal to 1 by 4 pi epsilon naught q by r square. This is the electric field due to a point charge. If so many charge and remains, then you can apply also superposition principle. But if the charge distributed uniformly along a linear, along a particular or within a particular surface or within a particular volume, then you have to take the help of Gauss's theorem. So Gauss's theorem is phi equal to closed integration E dot ds, and this is the definition, and you can write q by epsilon naught. So phi net equal to q inside by epsilon naught. Inside means the charge within the closed surface. So to calculate electric field P at point P, we have to consider a Gaussian surface. So Gaussian surface, so this is the Gaussian surface. This is the Gaussian surface, and it is imaginary. Suppose that particular point lie on that surface. So this is the Gaussian surface. This is the Gaussian surface, and this is infinitely extended. So let us consider a Gaussian surface. Let us consider a Gaussian surface such that the observation point lie on the surface. So that particular point at which you have to calculate electric field, it must be on the surface of the Gaussian surface. So next you have to apply Gauss's theorem. So flux phi equal to, since that particular charge can create an electric flux field lines along this direction. So this particular surface is like a cylinder, and you can write down as the net flux equal to closed integration of electric field E dot ds. Closed integration of electric field, and to calculate that particular closed integration, then you can think that particular cylinder is consist of, if suppose this is the cylinder, then this is a particular surface and the outward normal is along that particular direction. So these will be the outward normal, and you can name as n cap, but the electric field is along this direction. But for that particular surface, the outward normal is along that particular ones, but the electric field is along this direction. So this is the direction of electric field, this is the direction of electric field, and n cap is the outward normal. So for we can take a 3, or we can break this particular closed integration into 3 open integration. That is the open integration 1, that is E dot ds, and this is for that particular surface. This is 1, and this is 2, and this is 3. So for that particular cylinder, it consists of 3 surfaces. That is 1, and the second one is curved one, and the third one is also a circular surface. So this is 1 plus closed integration E dot ds, and this is 2 plus the closed integration. It is not closed, it is open integration. So this is open. So this one and that one and this one. So this plus this plus this, that is equal to a closed integration of E dot ds. So you can get net flux. So students, if we analyze that particular one number surface, then we see that E is the magnitude and R cap is a unit vector that represents the direction of the electric field, and ds is the area, and here also n cap represents the outward normal. So one number surface is like that. And for the second, and it is similar to that one, you can write here as E and R cap and ds and n cap, and for the third one is also E, R cap and ds and n cap. So this is 3. So this is 3. And so the next line is the integration of EDS and R cap dot n cap. What is the value of R cap dot n cap? So R cap is a unit vector dot n cap, that is equal to 1 into cos theta. So theta, where the one number surface is, that is 90 degree. So cos 90 means 0. So R cap dot n cap equal to 0. So the one number integration vanished, and that is the second integration. This is EDS cos 90 degree plus, that is EDS for the second one. It is if we take a small area, then it is the n cap is along this direction and electric field is also along this direction. So this is theta equal to, here it is 0 degree, here theta equal to 90 degree, and here theta is also 90 degree. So that students, that linear distribution of charge, if you imagine a cylinder and there is a linear distribution of charge at along the perpendicular, along the axis, then it can create some field, electric field lines along all the direction, and all the electric field lines are penetrated on the closed surface, but remaining the particular ones. So this is 1 and this is 2, EDS cos 0 degree, and then integration 3, that is EDS cos 90. If the field lines are generated, then it can only penetrate the curved surface, and for that particular surface there is no flux. So 1 integration 1 and 3 vanish, and E dot ds, that is the contribution of all the fluxes comes from that particular closed surface, that is 2 EDS cos 0 degree. So the net flux is equal to all the contribution of flux is from surface 2. So E phi net is equal to E dot ds, that is for the surface 2. So the next concept, this is we get from the definition. But from Gauss's theorem, phi equal to q inside by epsilon naught. So what is the amount of charge within that particular line. So we can write that dq equal to lambda into rho. So the total charge within this, if we take the whole length, then you can get q equal to lambda l. That is lambda l by epsilon naught. Lambda l by epsilon naught. So this is equation 2, and if we equal this one with that particular one, so this is EDS equal to lambda l by epsilon naught, or E, that is integration of EDS. E into integration of ds means the curved surface area. So it is 2 pi RL. 2 pi RL is the curved surface area of the cylinder, curved surface area of cylinder. So lambda l by epsilon naught. So E into 2 pi RL, E into 2 pi RL by this one, and that is electric field equal to, that is electric field equal to L and L cancel, so lambda by 2 pi epsilon naught. And if we that particular constant if you consider, then if we write 4 pi epsilon naught, then you have to multiply 2 in the numerator, that is 2 lambda by r. This is the electric field. So we can place, this is kappa 2 lambda by r, and this is the electric field. So the kappa is, we know that this is 9 into 10 to the power 9, and this is Newton meter square by Coulomb. Newton meter square by Coulomb square. So F equal to 1 by 4 pi epsilon naught Q1 Q2 by r square. So Newton meter square by Coulomb square. This is the unit just of this one. You can place that particular. So electric field equal to kappa 2 lambda by r. So if we take the electric field and the distance, then you can show that the electric field is inversely proportional to. So if you imagine that this is the particular linear distribution of charge, and if you go away from that once, then the electric field decreases from all sides. If you go for that particular one, then you can also electric field decreases. So electric field decreases if that is the particular charge distribution. If you go from ahead of this one, then the electric field is also decreasing, and if you go along this particular direction, and it is a three-dimensional concept, and if you go around that particular one, then you can the electric field is decreasing from all sides. So you can easily calculate electric field at a particular point with the help of Gauss's theorem. So again, if we take another example for that concept, or suppose take a numerical. So calculate electric field due to a linear distribution of charge density 2 coulomb per meter at a distance 2 meter from the linear distribution of charge. So students, this is the linear distribution of charge, and the value of lambda is given, lambda equal to coulomb by meter cube by L. So this is the lambda is given, and you have to calculate electric field at 2 meter from this one. So electric field equal to, you know, that kappa into 2 lambda by r. Kappa into 2 lambda by r. So here kappa equal to 9 into 10 to the 9 is the Coulomb proportionality constant, and 2 into lambda is 2 and the distance is 2. So 18 into 10 to the power 9 Newton by Coulomb. Newton by Coulomb is the unit. So it is so simple. If you you want to calculate the electric field intensity due to linear distribution of charge, then you easily follow that particular formula. Then E equal to kappa to lambda by r. Okay. So take another numericals. Take another numericals, but if we go for a conceptual derivatives, let's take as suppose this is a Cartesian coordinate. Cartesian coordinate, and there is the electric field along this direction. There is an electric field, uniform electric field along. It is not the function of r. Electric field along this direction, and if we placed a cylinder along this direction, x-axis, then what is the charge enclosed within this cylinder? What is the charge enclosed? What is the charge enclosed within the cylinder? What is the charge enclosed within the cylinder? Suppose students, so the electric field penetrate that particular surface and emerge from that one. When the electric field enters within this surface, then the flux linked phi 1 for that surface is E dot ds or E dot A. A is the area. Suppose A is the area of this one, and suppose you can take it as this is the radius, then you can easily the electric field dot, that is r cap dot area means pi r square into this is the outward normal direction. So if we take this is x axis, this is y, and this is z axis, then this is minus I cap. So the electric field is r cap is along x axis, that is this is the unit normal and this is a particular unit normal. So E into pi r square and r equal to I cap. Since the direction of the electric field is along x axis, so in place of r we can write I cap, and this is the minus sign. There is a minus sign here. This is a minus sign, and I dot I. So I cap dot I cap equal to 1. So the flux is E pi r square. E pi r square. Again, if we calculate the flux linked with this one, so this is phi 2 equal to E dot ds. E dot area. If you take a small area, then you have to replace it with ds vector. So E into r cap dot a vector, this is pi r square into the outward normal is along this direction, so this is I cap, and r is also I cap. So E into pi r square, and this is I cap dot I cap, that is 1. So the flux is this one. So the net flux, so phi net equal to, phi is a scalar quantity, so you have to take vectorial, not vectorial addition, you have to take just scalar addition. So phi 1 equal to minus of E pi r square, and the phi 2 is plus of E pi r square. So E pi r square, and this is cancelled, this one. So the net flux is equal to 0. And if we apply a Gauss's theorem, that is F net equal to Q by epsilon naught. Q by epsilon naught means Q inside the surface divided by epsilon naught. Then since the flux is 0, so flux into epsilon naught, that is Q inside, equal to 0. So there is no charge enclosed within that particular cylinder. Now think, students, when the electric field is uniform, then there is no charge enclosed within the cylinder. So conclusion, when there is a uniform electric field, then there is no charge within this region. When there is a uniform electric field, if the electric field is non-uniform, then the flux, the entering flux and the outgoing flux for a particular surface is not equal, and the outgoing flux emerging, and the emerging flux is more at that particular position with the entering flux. So we can say that it must be there is a charge inside that particular cylinder. But if there is a uniform electric field, then we can say that there is no charge enclosed within that particular one. So students, all the numericals related with that particular linear charge distribution or cylindrical concepts, this is, and I think that is the particular concepts, and and for the next day we discuss with the surface distribution of charge and volume distribution of charge. So let's continue the study and wait for the next class. Thank you.